Vega, the star quietly guiding our sense of time. There is a star about 25 light-years from here that has been used, for longer than most people realize, as a kind of fixed point. Not a landmark exactly, because it moves, like everything else in the sky, but a reference, a place where measurements begin. Its name is Vega, and it sits in the constellation Lyra, which is small and easy to miss if you are not looking for it. Vega itself is not easy to miss. It is the fifth brightest star in the night sky, and from most of the northern hemisphere, it is visible on every clear night of the year. A light year is the distance that light covers in 1 year. Light moves at about 186,000 miles per second, which means that in a single year, it crosses roughly 5.9 trillion miles. Vega is 25 of those distances away. That sounds enormous, and it is. But among the stars that are bright enough for us to see without a telescope, 25 light-years is considered close. Most of the stars visible on a clear night are hundreds or thousands of light-years away. Vega is practically next door. This closeness is part of the reason it appears so bright. A star's apparent brightness, the way it looks to someone standing on Earth, depends on three things. The first is the star's actual size. The second is its surface temperature. The third is how far away it is. Vega happens to score well on all three counts. It is about 2.5 times wider than the Sun. Its surface runs at roughly 9,600 degrees Kelvin, which is almost twice the temperature of the Sun's surface. And it is close enough that its light reaches us with very little dimming over the distance. The result is a star that puts out about 40 times more light than the Sun and delivers a good portion of that light straight to us. If you have seen it, you probably noticed that it is white, with a faint blue tint. That color comes from the temperature. Cooler stars tend to appear red or orange, hotter ones shift toward blue. Vega falls on the hot end of the scale, just past pure white and into the beginning of blue. Astronomers classify it as spectral type A0V. The A means it is a white star. The 0 means it is the hottest subclass within that group. The Roman numeral V means it is a main sequence star, which is the term for a star that is still in the middle portion of its life, steadily turning hydrogen into helium through nuclear fusion in its core. Lyra, the constellation that Vega belongs to, is one of the smaller ones. It covers about 286 square degrees of sky, which puts it 52nd out of 88 recognized constellations. Its shape, if you connect the right stars, looks like a small parallelogram attached to a triangle. Vega sits at one corner of that triangle, the brightest point in the pattern by a wide margin. The second brightest star in Lyra, called Sulafat, is more than 3 magnitudes fainter, which means Vega outshines it by a factor of roughly 15. Lyra is one of those constellations where a single star does most of the work. The name Lyra comes from Latin, and it means lyre, which is a small stringed instrument. In Greek mythology, the lyre in the sky was said to belong to Orpheus, a musician whose playing was so skilled that it could charm animals, bend trees, and even pause rivers. After Orpheus died, the story goes, Zeus placed his lyre among the stars. Vega marks the handle of that instrument. It is a fitting association, in a way, because Vega has been a kind of tuning fork for astronomy. Not musically, but in the sense that it has been used to calibrate, to set standards, to establish where 0 is. The name Vega itself comes from Arabic. The full phrase is An-Nasr al-Waki, which translates to the falling eagle or the swooping eagle. In older European texts, the star was spelled Vega, closer to its Arabic pronunciation. Over time, the W became a V, and the spelling settled into its current form. There is a small ongoing debate about how to say it. Some astronomers prefer Vega, which follows the older pronunciation. Others say Vega, which reflects how the letters look in modern English. Both are considered acceptable. The American Astronomical Society settled on Vega decades ago, but Vega is more common in everyday use, at least in the United States. The eagle reference is interesting because it connects to how other cultures saw the same region of sky. In ancient Egypt and in parts of India, the constellation we call Lyra was pictured not as a harp, but as a bird, a vulture, or an eagle swooping downward. The Arabic name preserved that older image. When the Greeks reinterpreted the same group of stars as a musical instrument, the bird imagery faded in the Western tradition, but it lingered in the name. Vega is also part of a much larger pattern that is not an official constellation, but is one of the easiest shapes to find in the sky. It is called the Summer Triangle, and it consists of 3 bright stars from 3 different constellations. Vega in Lyra forms one corner. Altair in the constellation Aquila, the eagle, forms another. Deneb in Cygnus, the swan, makes the third. From mid-northern latitudes, the Summer Triangle is visible in the evening sky from about June through December, though it is most prominent in July and August, when it passes nearly overhead. The 3 stars in the Summer Triangle are not physically related to each other. They only appear close together because of our line of sight from Earth. In reality, they are at very different distances. Vega is about 25 light-years away. Altair is closer, at about 17 light-years. Deneb is vastly farther, roughly 2,600 light-years from Earth. If you could somehow view these 3 stars from the side instead of from our position, the triangle would vanish completely. They are scattered across a huge volume of space, and the neat geometric shape they seem to form is an accident of perspective. This is true of all constellations, actually. The patterns we see in the night sky are not real structures. They are flat projections of stars that happen to line up from where we stand. 2 stars that appear right next to each other might be separated by hundreds of light-years in depth. The sky, in that sense, is a screen, and constellations are shapes drawn on that screen by our particular point of view. If Earth were somewhere else in the galaxy, the constellations would look completely different. Vega would still exist, of course, but it might not be grouped with the same neighbors, and it might not appear as bright, depending on the angle. But from here, from this specific location in space, Vega has been one of the most prominent objects in the sky for as long as humans have kept records, and probably for much longer than that. It has been given names in dozens of languages. It has been woven into myths on nearly every continent. And it has accumulated a long list of scientific firsts, a chain of moments where Vega happened to be the star that astronomers pointed their instruments toward when they tried something new. One of those firsts happened on the night of July 16 to 17, 1850, at the Harvard College Observatory. An astronomer named William Bond, working with a photographer named John Adams Whipple, aimed a 15-inch refracting telescope at Vega and used a process called daguerreotype to capture its light on a small metal plate. Daguerreotype was an early form of photography that involved coating a sheet of silver-plated copper with iodine vapor, exposing it to light, and then developing the image over heated mercury. The process was slow, and the results were fragile, but on that night it worked. The exposure lasted several minutes, and when the plate was developed, it showed a small mark of light. That mark was Vega. It was the first photograph ever taken of a star other than the sun. The daguerreotype process had already been used to photograph the moon 10 years earlier by John William Draper, but stars are far more difficult targets. They are point sources, meaning their light does not spread across a visible disk the way the moon's does. Capturing a single point of light on a chemically treated plate through a telescope in the middle of the night was a technical challenge that took years to solve. Vega was the breakthrough. 22 years later, in August of 1872, another astronomer chose Vega for another first. Henry Draper, who was the son of the man who had photographed the moon, aimed his own telescope at Vega and took a photograph not of the star's light directly, but of its spectrum. A spectrum is what you get when you spread a beam of light out into its component colors, the way a glass prism turns white light into a rainbow. Every star produces a spectrum, and within that spectrum, certain colors are missing. They show up as dark lines, thin gaps in the rainbow where specific wavelengths of light have been absorbed. These dark lines are called absorption lines, and they act as a kind of fingerprint. Different elements absorb different wavelengths, so by reading the pattern of dark lines in a star's spectrum, you can figure out what the star is made of. Draper's photograph of Vega's spectrum was the first time anyone had captured a star's absorption lines on film. The lines he recorded turned out to be hydrogen. Specifically, they were part of a pattern called the Balmer series, which is produced when electrons in hydrogen atoms drop from higher energy levels to a specific lower one. Each drop releases light at a precise wavelength, and each of those wavelengths corresponds to one of the dark lines in the spectrum. Draper could not have known all of that at the time, because the Balmer series was not formally described until 1885, more than a decade later. But his photograph was the beginning of a kind of reading. It was the moment when astronomers started being able to look at a star's light and determine from millions of miles away what that star was made of. Vega kept showing up at these turning points, among the first stars to have its distance measured through parallax, among the first single main sequence stars detected as an X-ray source in 1979, the first star found to have a disk of dust orbiting it in 1983. These were not all planned. In many cases, Vega was chosen simply because it was bright, nearby, and well-positioned in the sky. It was convenient. But the effect of all these choices, accumulated over more than a century, was that Vega became one of the most studied objects outside our own solar system. Astronomers have described it as arguably the most important star in the sky after the Sun, which is a strong statement for a single point of light 25 light-years away. Part of what made Vega so useful for science was its apparent stability. Most things in the sky change in one way or another. Stars brighten and dim over cycles. Planets wander. Nebulae shift slowly over centuries. But Vega, for a long time, seemed to hold steady. Its light output appeared constant enough that astronomers could rely on it as a baseline. This quality made it ideal for one of the most fundamental tasks in observational astronomy, which is deciding how bright things are. The system astronomers use to measure brightness is called apparent magnitude. It goes back to the ancient Greeks, who sorted the visible stars into 6 groups. The brightest were called first magnitude. The faintest that could be seen with the naked eye were called sixth magnitude. In the 19th century, this rough scale was formalized mathematically. Each step in magnitude corresponds to a brightness change of about 2.5 times. A first magnitude star is about 2.5 times brighter than a second magnitude star, which is about 2.5 times brighter than a third magnitude star, and so on. The scale also extends in the other direction. Very bright objects can have magnitudes of 0 or even negative numbers. The Sun, for example, has an apparent magnitude of about negative 26.7. Any measurement scale needs a reference point, a place where 0 is. For apparent magnitude, that reference point has historically been Vega. Astronomers originally used Polaris, the current North Star, as their standard, assigning it a magnitude of 2, but they eventually discovered that Polaris is a variable star, meaning its brightness fluctuates slightly over time. A measuring stick that changes length is not very useful. So they switched to Vega, which appeared more stable, and assigned it a magnitude very close to 0. The technical value is 0.03, but for practical purposes, Vega is magnitude 0. It is the anchor. This means that when astronomers describe any other star's brightness, they are, in a sense, comparing it to Vega. A star with a magnitude of 1 is about 2.5 times dimmer than Vega. A star with a magnitude of 5 is about 100 times dimmer. A star with a magnitude of -1 is about 2.5 times brighter. The entire brightness scale radiates outward from Vega's level of light, like rings around a stone dropped in water. In the 1950s, this idea was made even more precise with the introduction of the UV photometric system, which measures a star's brightness through 3 different filters: ultraviolet, blue, and visible. Vega was one of 6 stars of the same type that were used to define the baseline for this system. The idea was that for these reference stars, the brightness measured through each filter should be the same. No color bias, no lean toward blue or red. Just a flat, even output across the visible range of light. Vega, with its smooth and relatively featureless spectrum, was well suited for this. The Hubble Space Telescope and many other instruments use a related system called VGMAG, in which Vega is defined as having a magnitude of exactly 0 at every wavelength. This is a slight simplification of reality, but it works well enough for most purposes, and it means that Vega is embedded in the calibration of some of the most powerful telescopes ever built. When scientists point the Hubble at a distant galaxy and report its brightness, the number they give is implicitly anchored to the light of a single star in the constellation Lyra. Since 1943, Vega has also served as an anchor for spectral classification. Its spectrum, the specific pattern of absorption lines, and the overall shape of its light output is used as a reference standard for classifying other stars. If an astronomer needs to determine what type a newly observed star belongs to, one of the things they might do is compare its spectrum to Vega's. The system is more complex than a single comparison, of course, involving many reference stars and detailed criteria, but Vega sits near the starting point of that framework. All of this amounts to something unusual. Vega is not the biggest star, or the hottest, or the closest, or the most massive. It is not remarkable in any single physical dimension, but it has ended up as a fixed point in human understanding, a star that defines where zero is, where measurement begins, where categories are anchored. Astronomers did not choose Vega for this role because of some deep cosmic significance. They chose it because it was there, because it was bright and steady and convenient. But once those choices were made, they accumulated. Vega became the star that other stars are compared to. It became the baseline. There is something interesting about that, because Vega also serves as a kind of baseline for time, though on a much longer scale. This has to do with a phenomenon called precession, which is a slow wobble in the direction that Earth's axis points. Earth spins on an axis, an imaginary line that runs from the North Pole to the South Pole. That axis is tilted about 23.4 degrees relative to the plane of Earth's orbit around the Sun. This tilt is what gives us seasons. When the northern hemisphere is tilted toward the Sun, it is summer there and winter in the southern hemisphere. 6 months later, the situation reverses. The tilt stays roughly the same over long periods, but the direction of the tilt changes. Imagine a spinning top on a table. If the top is perfectly upright, it spins cleanly, but if it is tilted, even slightly, the top does something else in addition to spinning. Its axis traces a slow circle. The top continues to spin fast, but the direction it leans sweeps around gradually. This secondary motion is called precession, and Earth does the same thing. The cause in Earth's case is gravity. Earth is not a perfect sphere. It is slightly wider at the equator than from pole to pole by about 43 kilometers. This equatorial bulge means there is a little extra mass around the middle. The Sun and the Moon both pull on that bulge, and because Earth is tilted, the pull is not perfectly balanced. The result is a slow twisting force, a torque, that does not change the angle of the tilt, but causes the axis to rotate. One full cycle takes about 25,772 years. This is sometimes rounded to 26,000 years. As the axis rotates, the point in the sky that it aims at moves. Right now, Earth's axis points very close to a star called Polaris in the constellation Ursa Minor. Polaris is within about 1 degree of the exact north celestial pole, which is why it has served as the North Star for the past several centuries. Travelers, sailors, and navigators have used it to find north because it barely moves over the course of a night, while everything else in the sky appears to wheel around it. But Polaris has not always been the North Star, and it will not always be. The pole traces a large circle on the sky, and different stars take turns being closest to that circle's current position. About 5,000 years ago, when the Egyptian pyramids were being built, the nearest bright star to the pole was Thuban in the constellation Draco. Some of the pyramids have internal shafts that point toward where Thuban would have been at the time of their construction. Around 2000 BCE, Kochab in Ursa Minor was roughly in the right position, though it was never as precise a pole star as Polaris is today. In about 3,200 years from now, the pole will have moved to a point near a star called Gamma Cephei. And in about 12,000 years, around the year 14,000, the pole will be near Vega. Vega will not be as perfectly aligned with the pole as Polaris is now. At its closest, Vega will still be about 5 degrees away from the exact north celestial pole, which is about 10 times the width of the full moon, but it will be by far the brightest pole star of the entire 26,000-year cycle. Polaris is a moderately bright star with a magnitude of about 2. Vega, at magnitude 0.03, is roughly 6 times brighter. When Vega takes over as the approximate pole star, it will be a more conspicuous marker than anything the Northern Hemisphere has had in the past several thousand years. The last time Vega held this position was around 12,000 BCE, roughly 14,000 years ago. That was toward the end of the last ice age. Large parts of North America, Europe, and Asia were still under glacial ice. Sea levels were significantly lower than today, and the world's coastlines were in different places. Humans were living as hunter-gatherers in most regions, though the earliest experiments with agriculture were beginning in parts of the Middle East. The world looked almost nothing like it does now. But if a person in that era had looked straight up on a summer night and happened to notice which bright star sat nearest to the point where the sky seemed to turn, it would have been Vega. This is one of those facts that is easy to state but difficult to fully absorb. The same star that ancient humans might have used for navigation will, in another 12,000 years, return to roughly the same position. The cycle repeats. It has been repeating for as long as Earth has had its current shape and tilt, which is to say for hundreds of millions of years, though the stars involved change over geological time as they move through the galaxy. Hipparchus, a Greek astronomer working around 130 BCE, was the first person known to have detected precession. He did it by comparing his own measurements of star positions to older records kept by Babylonian astronomers. He noticed that the positions had shifted slightly in a consistent direction, and he calculated an approximate rate of drift. He could not explain why it happened, because the physics of gravity and rotational dynamics were not understood for another 18 centuries. That explanation came from Isaac Newton, who showed that the gravitational pull of the sun and moon on Earth's equatorial bulge would produce exactly the kind of slow axial rotation that Hipparchus had measured. There is a monument to this cycle, built into the western flank of the Hoover Dam in Nevada. When the dam was completed in the 1930s, the Bureau of Reclamation commissioned an artist named Oscar Hansen to design a plaza for the site. The most photographed features of that plaza are two large bronze sculptures with outstretched wings. But beneath the feet of the visitors who take those photographs, built into the terrazzo floor, is a celestial map. It records the positions of the stars and planets as they appeared on the night the dam was dedicated, and it encodes that information using the precession cycle. The idea was to create a marker that would remain legible not for decades or centuries, but for tens of thousands of years. By combining the positions of the planets with the known rate of precession, a future observer could work backward and determine the exact date the dam was built, even if all written records were lost. The floor is, in effect, a 26,000-year clock, and the fact that it works at all is because precession is so reliable. The precession cycle connects Vega to something larger than its own physical properties. It turns Vega into a kind of hand on a cosmic clock, a mark of where we are within a rotation that most people never notice. Right now, the hand points toward Polaris. In the past, it pointed near Thuban. In the future, it will point near Vega again. The cycle does not care about human history. It operates on its own timescale, indifferent to empires, technologies, or species. But it does provide a framework, a way of anchoring ourselves within time periods that are too long for calendars or clocks. The Romans used Vega for a smaller version of the same idea. For them, the time of year when Vega set below the western horizon marked the beginning of autumn. It was a practical observation. You watch the sky, you notice when certain stars appear and disappear, and you use those appearances to track the seasons. Before mechanical clocks, before printed calendars, the sky was the primary timekeeping device. Vega's annual rise and fall helped mark the passage of the year. In China, Vega played a different kind of timekeeping role, one woven into a story rather than a calendar. In Chinese tradition, Vega is known as Zhainu, the weaving girl. According to the story, the weaving girl was a goddess who wove the clouds and light of the sky. She fell in love with a mortal cowherd, represented by the star Altair, which sits on the other side of the Milky Way. In the story, the Milky Way is called the Celestial River, and it separates the two lovers. They are allowed to meet only once a year, on the 7th night of the 7th lunar month, when a bridge of magpies forms across the river to bring them together. This story is celebrated as the Kixi Festival in China. A version of it exists in Japan, where it is called Tanabata, and in Korea, where it is called Chilseok. The details change between the versions, but the basic structure is the same. Two stars on opposite sides of the Milky Way, separated by a river of light, reuniting once a year. The festival marks that reunion, and it has been observed for centuries. There is a coincidence embedded in the story, though it was not understood as such at the time. Vega and Altair really are on opposite sides of the Milky Way band as seen from Earth. The Milky Way runs between them, a pale stripe of diffuse light that is actually the combined glow of billions of distant stars in the disk of our galaxy. The two stars appear to be separated by this band, and the myth took that visual separation and turned it into a narrative. The science and the story line up, not because the storytellers knew about galactic structure, but because they were paying attention to the same sky. The Assyrians in their time called Vega Diansame, which translates roughly as the judge of heaven. In Babylonian astronomy, it may have been known as Dilgun, the messenger of light. Each culture that named it was doing so from the same planet, looking at the same photons, but fitting what they saw into their own frameworks of meaning. The star did not change, the names did. Vega is part of an unusual class of objects in that its importance is not entirely about what it is. It is also about where it is, how bright it is, and how steadily it shines. These are not dramatic qualities, they are practical ones. Vega is the kind of thing that works well as a reference because it does not call attention to itself. It does not flicker dramatically. It does not change color. It does not have a companion star that periodically eclipses it. It is just there, consistently, night after night, at about the same brightness, in about the same position relative to other stars. That consistency, though, is a slight illusion. Vega does vary in brightness, but by a very small amount. It is technically classified as a delta scuti variable, which means it pulsates slightly, brightening and dimming over a cycle of about 0.2 days. The variation is less than a tenth of a magnitude, which is far too small to notice with the naked eye. For most purposes, including the calibration work it has been used for, this variation is negligible, but it is there. Vega is not perfectly steady, it is just steady enough. The star also has a physical feature that is not visible from Earth, but that affects how we perceive it. Vega spins fast, very fast. The sun rotates on its axis about once every 28 days. Vega completes a full rotation in roughly 12.5 hours. Its equatorial speed is about 236 kilometers per second, which is fast enough to distort its shape. Instead of being a sphere, Vega is an oblate spheroid, wider at the equator than from pole to pole. The equatorial radius is about 19% larger than the polar radius, which is a substantial difference for a star. This rapid rotation creates something unexpected. Because the equator is farther from the core than the poles are, and because the equatorial surface is stretched over a larger area, it is cooler there. Vega's poles are hotter than its equator by a significant margin, roughly 10,000 Kelvin at the poles versus about 7,600 Kelvin at the equator. If you could see Vega from the side, looking at its equator, it would appear dimmer and redder than it does from where we sit. But by coincidence, Vega's rotation axis is pointed almost directly at Earth. We are looking nearly straight down at one of its poles, at the hottest and brightest part of the star. This polon orientation is one of the reasons Vega appears as bright and as blue-white as it does. From a different angle, it would look like a somewhat different star. This is not something anyone on Earth could have known until modern astronomy made it possible to measure. For all of human history before that, Vega was simply a bright white star. The fact that we happen to be staring at its pole and that this makes it appear brighter and bluer than it would otherwise is a quirk of geometry. It does not change anything about the star itself. But it does mean that our particular view of Vega, the one that has informed all of those myths and measurements and calibration systems, is not a neutral view. It is a specific one, shaped by the angle of the line between here and there. Vega is a young star by most standards. Its estimated age is somewhere around 450 to 700 million years. The range is wide because age is one of the harder things to pin down for a star, especially one that is not part of a cluster whose formation date can be calculated more precisely. For comparison, the Sun is about 4.6 billion years old. Vega is roughly 1/10 that age. It has existed for less time than complex life has been on Earth. Dinosaurs had already appeared and disappeared long before Vega formed. Despite being younger, Vega is burning through its fuel faster. This is a general rule in stellar physics. More massive stars use up their hydrogen more quickly. The Sun, at one solar mass, has an expected main sequence lifespan of about 10 billion years. Vega, at about 2.1 solar masses, has a main sequence lifespan of roughly 1 billion years. It is currently somewhere near the middle of that life, which means it has a few 100 million years of stable hydrogen burning left. After that, it will exhaust its core hydrogen, expand into a red giant, shed its outer layers, and eventually become a white dwarf, a dense remnant about the size of Earth, but with a mass close to the Sun. That future is a long way off, but it is certain, at least within the limits of what stellar physics can predict. Every star that burns hydrogen in its core will eventually run out. The timing depends on mass. The outcome depends on mass. And for Vega, the clock is ticking faster than it does for the Sun, even though Vega started later. In 1983, a satellite called the Infrared Astronomical Satellite, usually abbreviated as IRAS, detected something around Vega that no one had seen around any other star before. It found an excess of infrared radiation, more than what the star alone should have been producing. Infrared light is a form of light with wavelengths longer than what the human eye can detect. It is often associated with heat. When small particles, like dust grains, are warmed by a nearby star, they emit infrared radiation. The extra infrared coming from Vega's direction was consistent with a disk of dust surrounding the star, a ring of tiny particles heated to modest temperatures by Vega's light. This was the first circumstellar dust disk ever discovered around a main sequence star. It was a significant finding because dust disks are thought to be either the raw material from which planets form or the debris left over from that process. In our own solar system, the Kuiper Belt, a region beyond Neptune's orbit filled with icy and rocky objects, is a rough analogy. Vega's dust disk extends from roughly 80 to 800 astronomical units from the star. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the disk stretches from about 80 times that distance to about 800 times that distance. It is large. The discovery of Vega's dust disk opened a new field of study. Stars that show a similar infrared excess are now called Vega-like stars, using Vega as the prototype. The question of whether there are actual planets in the disk has not been conclusively answered. Some early observations suggested perturbations in the dust that could indicate a large planet, but later observations with more precise instruments, including the James Webb Space Telescope, found the disk to be smooth and symmetric, with no clear signs of massive planets shaping it. There may be smaller planets, perhaps Neptune-sized or smaller, orbiting closer to the star, but they have not been directly detected. The dust itself is thought to come from ongoing collisions between smaller objects, asteroids and comets, and chunks of rock grinding against each other and producing fine debris that spreads through the disk. Vega's dust disk has another implication, which is that the star system is probably still in an early and somewhat chaotic phase of development. In our solar system, the period of heavy bombardment, when leftover planetesimals were slamming into planets and moons, ended about 3.8 billion years ago. In Vega's system, that kind of activity may still be ongoing, producing the dust that IRAS detected. The system is young enough for that. There is one more physical detail about Vega that is worth mentioning, because it connects to the broader picture of what the star is and how it differs from the Sun. Vega has a lower metallicity than the Sun. In astronomy, metallicity does not just refer to metals in the everyday sense. It refers to all elements heavier than helium. Stars are made mostly of hydrogen and helium, but they also contain trace amounts of heavier elements, things like carbon, oxygen, iron, and silicon, which were produced by earlier generations of stars and distributed through space when those stars exploded. The Sun's atmosphere contains a certain abundance of these heavier elements. Vega's atmosphere has only about 32% of that abundance. This does not mean Vega is deficient. It just means it formed from a cloud of gas that had a slightly different composition than the cloud that produced the Sun. The difference is consistent with what you would expect for a younger star in a slightly different part of the galaxy. It does not dramatically affect Vega's behavior, but it does affect the details of its spectrum and its internal structure in ways that astronomers find useful for testing their models of how stars work. Vega is also getting closer, not quickly in human terms, but steadily, over timescales that are long even by astronomical standards. Our solar system is moving through space in a direction that happens to be roughly toward Vega. This direction is called the solar apex. The motion is not caused by Vega pulling on us. It is simply the combined gravitational effect of everything in our galactic neighborhood, resulting in a trajectory that currently carries us in Vega's general direction. In about 210,000 years, Vega will become the brightest star in the night sky. It will reach its closest approach to us in roughly 264,000 years, at which point it will be about 13.2 light-years away, roughly half its current distance. At closest approach, its apparent magnitude will be about -0.81, which is bright, though still not as bright as Sirius is now. Sirius currently shines at about -1.46. But Vega will hold the title of brightest star for a long stretch, and after reaching peak brightness around 290,000 years from now, it will remain the brightest star in the sky for another 270,000 years or so after that. These are not round numbers. They are estimates based on the current relative motions of our solar system and Vega through the galaxy. None of this motion is perceptible on a human timescale. The change in Vega's brightness over 1,000 years or even 10,000 years is far too small to notice without instruments. But the motion is real, and it means that the Vega we see tonight is not quite the same as the Vega that people saw 10,000 years ago, and it will not be quite the same as the one people will see 10,000 years from now. It is getting brighter, getting closer, and its position in the sky is shifting, all very slowly, as both it and we move through the galaxy on our separate paths. There is a meteor shower connected to Vega, though not physically caused by it. Every year in late April, around the 21st and 22nd, the Lyrid meteor shower occurs. The meteors appear to radiate from a point in the sky near Vega, in the constellation Lyra, which is why the shower is named the Lyrids. The actual source of the meteors is not the star, but a comet called Comet Thatcher, which last passed through the inner solar system in 1861 and will not return for another couple of centuries. As the comet orbits the Sun, it leaves behind a trail of tiny particles, bits of ice and rock. When Earth's orbit passes through this trail, the particles enter the atmosphere at high speed and burn up, producing streaks of light. The connection to Vega is purely directional. The meteors seem to come from that part of the sky because of the angle at which Earth moves through the debris trail. But the association has given Vega yet another link to annual timekeeping. The Lyrids are one of the oldest recorded meteor showers. Chinese astronomers noted them as early as 687 BCE, more than 2,700 years ago. That makes the Lyrids older as a recognized and recorded event than most human institutions. Each April, the same shower returns from the same apparent point in the sky as Earth crosses the same trail of debris on its annual orbit. It is a small cycle, 1 year long, layered on top of the much larger cycle of precession. Vega sits at the intersection of both. It marks the approximate point in the sky where the Lyrids originate, and it marks a position in the 26,000-year wobble of Earth's axis. One cycle takes a year, the other takes 260 centuries. Both are consistent, repeating, and tied to the same star. The idea of measuring the distance to a star was, for a long time, considered impossible. Stars were known to be far away, but how far was a matter of speculation. The ancient Greeks debated it. Aristarchus of Samos, around 270 BCE, proposed that the Earth moved around the Sun, and he recognized that if this were true, nearby stars should appear to shift positions slightly as Earth moved from one side of its orbit to the other. He looked for this shift and could not find it, which he correctly attributed to the stars being extremely far away, so far that the shift was too small to measure with the instruments available to him. The failure to detect stellar parallax was actually used as an argument against the heliocentric model for centuries. If Earth really orbited the Sun, critics said, surely the stars would show some displacement. They did not seem to, and the simplest explanation was that Earth did not move. Resolution, of course, was that the stars really are that far away. The parallax shift of even the nearest stars is tiny, less than 1 second of arc for any star, which is a smaller angle than the eye can resolve and smaller than any instrument could reliably measure until the 19th century. When Struve attempted to measure Vega's parallax in the late 1830s, he was using one of the best telescopes of the era, a large refractor at the Dorpat Observatory in what is now Estonia. His technique involved observing Vega repeatedly over the course of a year and comparing its position to that of fainter, presumably more distant, background stars. The expected shift was a tiny wobble back and forth, in sync with Earth's orbit. Struve published a parallax value in 1840 that placed Vega at roughly the correct distance. His measurement was in the right ballpark, but the uncertainties were large, and his methods were questioned. Bessel's measurement of 61 Cygni, published in 1838, used a different method that was considered more rigorous, and Bessel is generally credited with the first reliable stellar parallax. The distinction matters less now than it did then. Both measurements were correct in their broad conclusions. Stars are light years away. Vega is about 25 of those light years from here. What matters is that the question was answered at all, and that Vega was one of the first candidates chosen. The reason Vega was a good candidate is the same reason it has been chosen for so many other things. It is bright, which makes it easy to observe with precision. It is nearby, which means its parallax shift is relatively large, and it is well placed in the sky for observers in the northern hemisphere. These are not deep cosmic reasons, they are practical ones. Astronomers work with what they can see, and Vega is easy to see. The modern value for Vega's parallax, measured by the Hipparcos satellite in the 1990s, is 0.13 seconds of arc. To put that in perspective, 1 second of arc is the angle subtended by a dime viewed from about 2 miles away. Vega's parallax is about 1/8 of that. It is the kind of measurement that requires not just good instruments, but careful statistical analysis, correction for atmospheric distortion, and accounting for the star's own motion through space. The Hipparcos satellite, which operated from Earth orbit and was therefore free from atmospheric interference, was able to measure parallaxes for more than 100,000 stars, with precisions on the order of 1,000th of a second of arc for the brightest ones. Vega's distance, as determined by Hipparcos, is 25.04 light-years, give or take a small fraction. That level of precision would have been inconceivable to Struve. His measurement was made with a brass telescope, using eyepieces and manual recording. The Hipparcos measurement was made with a space-based optical system, using digital detectors and computer processing. Between the two lies about 150 years of technological progress, all of which was built, in part, on the foundation that Struve and Bessel and their contemporaries laid. You cannot build a precision satellite without first establishing that the thing you want to measure exists and that it is measurable in principle. Struve's imperfect measurement of Vega's parallax was one of the steps in that chain. There is a successor to Hipparcos called Gaia, a European Space Agency satellite launched in 2013 that is measuring the positions, distances, and motions of over 1 billion stars with even greater precision. Gaia's data has refined the distance measurements for many stars, including nearby ones like Vega. The improvements are incremental at this point. The distance to Vega is not going to change significantly from the value established by Hipparcos. But the precision keeps improving, and with it, the ability to use Vega and other nearby stars as stepping stones for measuring distances to more remote objects. Distance measurement in astronomy works like a ladder. Each rung depends on the one below it. The first rung is parallax, which works for stars within a few thousand light-years. Beyond that, other methods take over, methods that rely on properties like the intrinsic brightness of certain types of stars, the pulsation periods of variable stars, or the characteristics of supernovae. Each of these methods is calibrated using objects whose distances are already known from parallax. So the parallax measurements of nearby stars, including Vega, propagate outward through the entire distance ladder. A small error in the parallax of Vega, if it existed, would ripple through every subsequent measurement, affecting the estimated distances of galaxies billions of light-years away. This is another sense in which Vega is a reference, not just for brightness and not just for spectral classification, but for the basic question of how far away things are. The distance ladder begins with the nearest stars, and Vega is one of them. The way that Vega's light interacts with the instruments that observe it has changed over the centuries, even though the light itself has not. In 1850, Vega's photons hit a silver iodide plate and created a chemical change. In 1872, they passed through a prism and fell on a different kind of plate, one sensitive enough to record the spread of wavelengths. In 1983, they were detected by an infrared sensor aboard a satellite in Earth orbit. In the 2020s, they were captured by the gold-coated mirrors and infrared detectors of the James Webb Space Telescope, positioned 1 million miles from Earth at a gravitationally stable point called L2. Each of these instruments saw something different, not because Vega changed, but because the instruments were sensitive to different things. The daguerreotype plate could only record visible light and only the brighter portions of it. The spectroscopic plate could spread the light out and reveal its components. The infrared satellite could see wavelengths that are invisible to the eye and that do not pass through Earth's atmosphere. The Webb telescope can see with a combination of resolution and sensitivity that exceeds anything before it. What they all have in common is that they were pointed at Vega and that the photons they collected had been traveling for roughly 25 years. The instruments changed. The photons did not. They arrived carrying the same information they always had, stamped with the same hydrogen lines, the same overall energy distribution, the same faint infrared excess from the dust disk. The difference was in what could be read from that information, and that depended entirely on the reader, not the message. There is something steady about that. The message does not change. It has been the same message for millions of years, since before there was anyone around to receive it. It is a continuous broadcast, not aimed at anyone, not encoded for anyone's benefit, just the natural consequence of a hot object radiating energy in all directions. But the people who have intercepted it over the past few thousand years have found in it a surprising amount to read. Temperatures, compositions, distances, ages, rotation rates, dust structures. All from light. The amount of information that can be extracted from starlight is in some ways the central achievement of astronomy. And Vega, by being the subject of so many firsts and the reference for so many standards, sits at the origin of that achievement. It is not the most scientifically interesting star in the sky. There are stranger objects out there, neutron stars, black holes, stars on the verge of supernova, binary systems in tight orbit. Vega is not exotic. It is a moderately large, moderately hot, moderately young star with a moderately interesting dust disk. But its ordinariness is exactly what makes it useful as a reference. You do not want your measuring stick to be unusual. You want it to be typical, well-behaved, and stable. Vega is all of those things to a degree that has served astronomy well. The atoms in Vega are the same kinds of atoms that exist everywhere else. Hydrogen mostly, with some helium and trace amounts of heavier elements. The hydrogen in Vega's core was produced in the first few minutes after the Big Bang, about 13.8 billion years ago, when the universe was hot enough and dense enough for protons and neutrons to fuse into simple nuclei. The helium was produced in the same process. The heavier elements, the carbon and oxygen and iron and silicon that make up Vega's small but measurable metallicity, were produced later, inside other stars that lived and died before Vega formed. When a massive star ends its life in a supernova, it scatters those heavy elements into the surrounding gas and dust. The next generation of stars, forming from that enriched material, incorporates those elements into its own structure. Vega is one of those next-generation stars. It contains the ashes of stars that died before it was born, woven into its fabric alongside the primordial hydrogen and helium that have been around since the beginning. This is true of every star, and of every planet, and of every person. The iron in your blood was made in a star. The calcium in your bones was made in a star. The oxygen you are breathing was made in a star. These are well-established facts of nucleosynthesis, the process by which elements are built up inside stellar cores. Vega participates in this process right now. It is fusing hydrogen into helium in its core, and when it eventually dies, it will return a portion of its material to the interstellar medium, where it may become part of a future star or planet. But Vega is not massive enough to produce the heaviest elements. Only the most massive stars, those with more than about 8 times the mass of the Sun, end their lives in supernovae that scatter iron and other heavy elements. Vega, at about 2.1 solar masses, will end more quietly, as a white dwarf after passing through a red giant phase in which it sheds its outer layers as a planetary nebula. The expelled material will be enriched in some elements, particularly carbon and nitrogen, which are produced in the later stages of stellar evolution for stars of this mass. But it will not produce the explosive nucleosynthesis that creates elements like gold and platinum. The material that Vega ejects will drift outward into the interstellar medium and mix with the gas and dust already there. Over time, it may become part of a new nebula, a new cloud of gas that contracts under gravity and forms new stars. Those new stars will inherit Vega's contributions, along with the contributions of millions of other stars that have lived and died in the same neighborhood. The recycling of material between stars and the interstellar medium is one of the fundamental processes in the galaxy. It has been going on for billions of years and will continue for billions more. Vega's place in this cycle is modest. It is not a major contributor to the chemical enrichment of the galaxy. It is one star among hundreds of billions, doing what stars of its mass and composition do, converting hydrogen to helium and emitting light. Its significance to us is a local phenomenon, a product of our proximity to it and our history of using it as a reference. From a galactic perspective, Vega is unremarkable. From our perspective, it is one of the most thoroughly known and widely used stars in the sky. That difference in perspective is itself a useful thing to notice. What matters depends on where you stand. The Milky Way contains an estimated 200 to 400 billion stars. Vega is one of them. From the center of the galaxy, 26,000 light-years away, Vega would be invisible to the naked eye, lost among billions of others. From Earth, 25 light-years away, it is the fifth brightest thing in the night sky and the anchor of multiple measurement systems. The star is the same in both cases. The significance changes entirely based on the observer. Astronomers are aware of this, of course. They know that the stars they study most are often the ones that are easiest to study, not the most scientifically important. Bright, nearby stars get more attention than faint, distant ones, not because they are more interesting in absolute terms, but because they are more accessible. Vega is the extreme case of this. It has been studied so thoroughly that its name has become synonymous with calibration itself. The VGAMAG system is not named that way arbitrarily. It is named for the star because the star is the system. There is a moment in the history of any measurement system when the choice of reference point stops being a decision and starts being a tradition. The choice of Vega as the 0 point for brightness was a decision made in the mid-20th century by astronomers who needed a stable standard. But now, decades later, it is embedded in the design of instruments, the format of databases, the language of scientific papers, and the expectations of researchers. Changing it would not be impossible, but it would be disruptive, and there is no strong reason to do so. Vega works well enough. It has worked well enough for a long time, and so it persists, not because it is perfect, but because it is established. This is how many things in science work. The choice of units, the design of coordinate systems, the selection of reference frames. They are somewhat arbitrary at the start, but once adopted, they become part of the infrastructure, and replacing them requires more effort than maintaining them. The metric system replaced older systems of measurement in most of the world, but that transition took decades and is still not complete in some countries. The astronomical magnitude system, with Vega at its center, is far older and far more deeply embedded than any national system of weights and measures. It will be a long time before it is replaced, if it ever is. And so Vega remains in its dual role, a star in the sky doing what stars do, and a concept in the scientific literature embedded in the measurement of everything else. The two are connected by light and by the decisions that astronomers made over the past century and a half, and by the simple fact that when they needed a reference, Vega was the one they could see most clearly. Consistency of these cycles is one of the things that made astronomy possible in the first place. Before telescopes, before photography, before spectroscopy, the only tool astronomers had was patience. They watched the sky, recorded what they saw, and compared their records to those of earlier observers. The patterns they found, the rising and setting of specific stars at specific times of year, the slow drift of the pole across the centuries, the annual return of meteor showers became the foundation of a science. And Vega, because of where it sits and how bright it is, was part of many of those patterns. It is worth pausing on what it means for a star to be a reference point. In everyday life, reference points are things like doorframes and rulers and clocks. They are objects that stay in one place or change at a known rate so that other things can be measured against them. A ruler works because it does not shrink or grow. A clock works because its ticking is uniform. A reference star works the same way, but instead of measuring inches or seconds, it measures light. When astronomers assigned Vega a magnitude close to 0, they were saying, in effect, this is what zero brightness looks like. Everything brighter than this gets a negative number. Everything dimmer gets a positive number. The choice was somewhat arbitrary. They could have picked a different star, but once the choice was made, and once enough measurements were built on top of it, changing it became impractical. Vega's brightness became the starting line. Other systems have been developed since then that define zero magnitude using a precise numerical value of flux rather than any particular star. But the Vega-based system persists, especially in optical and near-infrared astronomy. The instruments may have changed, but the reference has proven durable. There is a parallel to how time itself is measured. The second, which is the fundamental unit of time in modern physics, was originally defined as a fraction of a day, which was defined by the rotation of Earth. But Earth's rotation is not perfectly uniform. It speeds up and slows down by tiny amounts due to tidal forces, earthquakes, and the redistribution of mass within the planet. So in 1967, the definition of the second was changed. It was redefined in terms of the frequency of radiation emitted by cesium-133 atoms, a value that does not change. The old reference, Earth's rotation, was replaced by something more stable. Something similar happened with Vega and the magnitude system. Vega was the original reference, and it served well for a long time, but as measurements became more precise, the small variability in Vega's light became an issue. The reference was shifted, in principle, to absolute flux values. But in practice, the Vega system remains in use, and the star's name is still attached to the calibration of major instruments. Vega is like a retired standard, still consulted, still respected, still embedded in the way things are done. The comparison between timekeeping and brightness measuring is not accidental. Both are about finding something stable enough to anchor a scale, and Vega has ended up on both sides of that comparison. It anchors the brightness scale directly, and it anchors a kind of deep timekeeping indirectly through its role in the precession cycle. It marks where the pole was, where it will be, and by implication, where it is now, relative to a 26,000-year sweep. If you step back far enough, the entire system of astronomical measurement starts to look like a web of reference points, each one stabilizing the others. Distances are measured using parallax, which requires knowing the baseline distance between two observation points. Brightness is measured using magnitude, which requires a 0 point. Spectra are classified by comparison to standard stars. Each piece depends on other pieces. And Vega sits near the center of several of these interlocking systems, not because it is extraordinary, but because it was there when the systems were being built. There is a practical way to understand parallax, because Vega was among the first stars for which it was attempted. Parallax is based on a simple idea. Hold a finger in front of your face and close one eye, then the other. Your finger appears to jump left and right against the background. This happens because your two eyes are a few inches apart, so they see the finger from slightly different angles. If you know the distance between your eyes and you measure how much the finger appears to move, you can calculate how far away it is. Astronomers do the same thing with stars, except instead of using two eyes, they use two positions of Earth in its orbit. In January, Earth is on one side of the Sun. In July, it is on the other side, about 186 million miles away from where it was 6 months earlier. That distance serves as the baseline. By observing a nearby star from these two positions and measuring how much it appears to shift against the more distant background stars, astronomers can calculate the star's distance. For most stars, this shift is tiny. Even for the nearest stars, the apparent movement is less than 1 second of arc, which is 1/3600th of a degree. Measuring such small angles was extremely difficult in the early 19th century. Friedrich Struve, a German-Russian astronomer, attempted to measure Vega's parallax in 1837 and published a value in 1840. His result was close to the modern value, which is 0.129 seconds of arc, corresponding to a distance of about 25 light-years. But his methods were questioned at the time, partly because another astronomer, Friedrich Bessel, had also measured a parallax for a different star called 61 Cygni, using methods that were considered more rigorous. Bessel is generally credited with the first reliable stellar parallax measurement. Struve's work on Vega is acknowledged, but remains debated. The point is not who got there first. The point is that Vega was one of the first stars that anyone tried to measure in this way. It was a natural candidate because it is bright, and because its nearness means its parallax shift is relatively large, at least by stellar standards. The measurement confirmed what brightness alone had already suggested. Vega is nearby, as stars go, and that nearness is part of why it has played such an outsized role in the history of astronomy. Light takes about 25 years to cross from Vega to here. That means the light arriving now left Vega about 25 years ago. This is true of every star, but it is worth noting because it creates a kind of time lag in our observations. We never see Vega as it is right now. We see it as it was a quarter century ago. For a star whose expected lifespan is measured in hundreds of millions of years, a 25-year delay is nothing. Vega 25 years ago was essentially identical to Vega today, but the principle is the same one that makes all astronomy a form of looking backward in time. The farther away something is, the older the light we receive from it. There are telescopes, like the James Webb Space Telescope, that can see galaxies whose light has been traveling for more than 13 billion years. Those galaxies are seen as they were near the beginning of the universe. Vega's light, by comparison, is practically fresh. It is an image from yesterday, cosmically speaking, but even yesterday's light carries information. The spectrum of Vega that Henry Draper photographed in 1872 was made of light that had left the star around 1847. The photograph captured not just the star's chemistry, but a specific moment in the star's life, frozen into the pattern of dark lines on a plate. Every observation of Vega, every photograph, every spectral measurement is a snapshot from a slightly different moment in the star's history. They are all recent moments, within a few decades of each other from the star's perspective, but they are technically different. The Vega that Bond and Whipple photographed in 1850 was not the same Vega that IRAS scanned in 1983, even though the differences between them are immeasurably small. The star aged by about 133 years, worth of hydrogen burning in between. That is nothing to Vega, but it is the entirety of modern astrophotography. The dust disk around Vega, the one discovered by IRAS, has been studied many times since 1983 with increasingly powerful instruments. Each time, it reveals a little more detail. The disk is not uniform. It has structure, regions where the dust is denser and regions where it is thinner, though recent observations suggest it is smoother than earlier studies thought. The James Webb Space Telescope, which began operations in 2022, looked at Vega's disk and found it to be unusually smooth, with no clear evidence of large planets carving gaps or creating asymmetries. This was a mild surprise. Many other dust disks around other stars do show these features. Sharp edges, gaps, and asymmetries in a dust disk often indicate that a planet is present, sweeping up material along its orbit and sculpting the disk like a hand dragged through sand. The absence of such features around Vega could mean that there are no large planets there. Or it could mean that any planets present are small enough that their gravitational effects on the dust are too subtle to detect with current instruments. Neptune-sized or smaller planets close to the star remain possible but unconfirmed. The uncertainty is itself interesting. Vega is one of the most observed stars in the sky, and yet the question of whether it has planets remains open. This is not unusual. Detecting planets around other stars is hard, especially when the planets are small or close to a bright host star. The methods that work well for finding large planets in wide orbits, such as direct imaging, and the methods that work well for finding close-in planets, such as the transit method, each have limitations. For Vega specifically, the polon orientation that makes the star appear so bright also complicates planet detection, because if there are planets orbiting in the plane of Vega's equator, they would be orbiting nearly face-on to us, which makes transit detection impossible. You can only detect a transit when a planet passes between you and the star. And that requires the orbit to be edge-on. So Vega keeps its secrets in that particular way. It is bright, nearby, and thoroughly studied, and yet no one can say for certain whether anything is orbiting it. The dust is there. The conditions for planet formation may be there, but the conformation is not. For now, the disk is just a disk, a ring of debris circling a star that may or may not have produced anything larger. Back to the matter of time. There are different scales at which Vega connects to the measurement of time, and they are worth separating out, because they span a range that is hard to hold in a single thought. At the shortest end, there is the annual return of the Lyrid meteor shower, a yearly event tied to Earth's orbit and the debris trail of Comet Thatcher. This has been observed and recorded for at least 2,700 years, based on Chinese records from 687 BCE. Once a year, in late April, Earth crosses through the same trail of particles, and the same patch of sky near Vega produces a scattering of bright streaks in the upper atmosphere. The shower is modest, usually producing about 10 to 20 meteors per hour at its peak, though occasionally it surges higher. It is consistent enough to predict, but variable enough to hold a mild uncertainty each year about exactly how many meteors will appear. One step longer is the cycle of the seasons, in which Vega's rising and setting have served as calendar markers. The Romans noted when Vega disappeared below the horizon as a sign that autumn had begun. This kind of observation, tracking the first or last appearance of a star relative to the sun's position, is called a heliacal observation, and it is one of the oldest forms of timekeeping. The Egyptians used the heliacal rising of Sirius to predict the annual flooding of the Nile. The Romans and Greeks tracked other stars for their own agricultural and ceremonial calendars. Vega's place in this tradition is less famous than Sirius, but it was part of the same practice. Then there is the cycle of precession, at 25,772 years, which moves the celestial pole through a full circle and brings different stars into the role of pole star. Vega is the brightest star along that path, and its tenure near the pole occurs roughly every 26,000 years. This cycle is too long for any single culture to observe directly, but it can be detected through careful comparison of records across centuries, as Hipparchus demonstrated. And then there is the approach of Vega itself, the gradual closing of the distance between our solar system and the star. This happens over hundreds of thousands of years, driven not by any special attraction, but by the ordinary drift of both objects through the galaxy. In roughly 210,000 years, Vega will overtake Sirius as the brightest star in the night sky. In 290,000 years, it will reach peak brightness. In 500,000 years, it will begin to fade again as our paths diverge. This is timekeeping on a scale that makes precession look short. Each of these cycles operates independently. The meteor shower follows Earth's orbit. The seasons follow Earth's tilt and its orbit. Precession follows the gravitational tug on Earth's bulge. Vega's approach follows the drift of stars through the Milky Way. They are separate mechanisms, governed by separate physics, running at separate rates. But they all happen to involve Vega, because Vega is where it is, bright enough and close enough to intersect with several of them at once. There is no special reason for this. It is not as though the universe arranged Vega to serve as a multi-scale timekeeper. It is a coincidence of position and brightness, but coincidences in astronomy can be useful. They give you a single object that connects to multiple systems, a kind of hub where different lines of measurement cross. Vega is that hub, not by design, but by circumstance. Astronomers sometimes use the phrase standard star to describe an object that serves as a reference for calibration. Vega is a standard star in a formal technical sense. Its brightness defines the zero point for photometric systems. Its spectrum anchors the classification of stellar types, but it is also a standard star in a broader, less formal sense. It is a star against which we can measure time, track motion, and mark our place in a cycle that predates human civilization. Chinese weaving girl myth encodes a version of this without any scientific language. Two stars, separated by a river of light, meeting once a year. The story contains an annual cycle, the festival, a spatial relationship, the two stars flanking the Milky Way, and a sense of deep patience, the lovers who wait. The science behind the story is different from what the story says, of course. Vega and Altair are not lovers. The Milky Way is not a river. Magpies do not form bridges in space. But the impulse to connect stars to time, to use what is visible in the sky as a marker for what happens on the ground, is the same impulse that led to the magnitude system, the spectral classification scheme, and the measurement of precession. The language is different. The underlying activity is the same. People look at the sky and use what they see to organize their experience of time. Vega's spectrum, the same one that Draper photographed in 1872, tells a specific kind of story about time if you know how to read it. The hydrogen absorption lines in Vega's spectrum, the dark lines that correspond to the Balmer series, are a record of a physical process. They form when light from the star's interior passes through its outer atmosphere, and atoms of hydrogen in that atmosphere absorb photons at precise wavelengths. Each absorption removes a narrow slice of color from the continuous rainbow of the star's light. The result is a spectrum with gaps. The wavelengths of those gaps are determined by the structure of the hydrogen atom, specifically by the energy differences between electron orbits. These energy differences are fixed by quantum mechanics. They do not change over time or from place to place. A hydrogen atom on Earth absorbs light at the same wavelengths as a hydrogen atom in Vega's atmosphere or in a galaxy a billion light years away. This constancy is what makes spectroscopy possible. If the rules of atomic physics were different in different places, you could never use a spectrum to identify what a distant star is made of. But the rules are the same everywhere as far as anyone has been able to measure. The hydrogen lines in Vega match the hydrogen lines in a laboratory on Earth. The laws of physics are the same there as here. This is a fact so basic that it is easy to overlook, but it underpins almost everything in modern astronomy. The ability to analyze light from distant objects and draw conclusions about their temperature, composition, motion, and distance all rests on the assumption that the same physics applies everywhere. Vega was one of the first stars where this assumption was tested and confirmed through Draper's spectrum and the decades of work that followed. The Balmer series, the set of hydrogen lines that Draper recorded, was formally described by Johann Balmer in 1885. He noticed that the wavelengths of the visible hydrogen lines followed a mathematical pattern, a formula involving simple integers. An electron dropping from the third energy level to the second emits red light. From the fourth level to the second, it emits blue-green light. From the fifth, violet. Each successive line moves closer to the next, converging toward a limit in the ultraviolet. Balmer found the formula by trial and error without knowing anything about electrons or energy levels which were not yet understood. The pattern was there in the numbers. The explanation came later. Vega's spectrum was one of the datasets that helped confirm Balmer's pattern. The dark lines in Vega's light matched the wavelengths predicted by the formula. This was not a surprise, because hydrogen is the most common element in the universe and spectral type. Stars like Vega are known for having strong hydrogen lines. But it was one more piece of evidence that the same simple mathematics governed light from both nearby lamps and distant stars. If you could somehow collect all the individual photons arriving from Vega and sort them by wavelength, you would find a distribution that peaks in the blue-white range and tapers off in both directions, toward the ultraviolet on one side and the infrared on the other. This shape is characteristic of a hot, dense object, and it follows a curve described by Max Planck in 1900. Planck's law says that the spectrum of a glowing object depends on its temperature and nothing else. The hotter the object, the shorter the peak wavelength. Vega, with a surface temperature around 9,600 Kelvin, peaks at a wavelength of about 300 nanometers, which is in the ultraviolet. The visible light we see is on the long wavelength tail of that peak. The infrared light from Vega, the light that revealed the dust disk, is even farther down the tail. At those wavelengths, Vega's own light is relatively faint, which is why the extra emission from the heated dust was detectable. The dust particles are much cooler than the star, and they emit their own radiation at longer wavelengths in the infrared. The IRAS satellite was designed to detect exactly that kind of emission, and when it found more infrared coming from Vega's direction than the star alone could explain, the dust disk was inferred. That discovery, in 1983, opened a new line of investigation in astronomy. Before IRAS found Vega's disk, no one had observed such a structure around a normal star. The Kuiper belt in our own solar system was not well understood at the time, and the idea that other stars might have similar belts of debris was theoretical. Vega's disk made it real. It was evidence that the processes that shaped our solar system, the accretion of dust into larger bodies, the collisions and fragmentations that produced debris, were happening elsewhere. Since then, hundreds of other stars have been found with similar disks. They span a wide range of ages and types. Some are young, with disks that may still be forming planets. Others are old, with disks that are probably leftover debris from planet formation that happened long ago. The study of these disks has become a major area of research, and the term Vega-like star, coined in the wake of the 1983 discovery, is still in use. Vega lent its name to the category. There is something quietly accumulative about Vega's role in all of this. It did not do anything dramatic. It did not explode or pulse wildly or produce an unusual signal. It simply sat in a convenient part of the sky, shining steadily, while astronomers kept choosing it as the target for their latest experiment. The result, over time, was that Vega became layered with significance, not because of what it is, but because of how often it has been looked at and what was found each time. It is still being looked at. The James Webb Space Telescope has observed it. Ground-based interferometers have studied its shape and rotation. Surveys of nearby stars continue to include it. Each new instrument sees a little more detail, resolves a little more structure, measures a little more precisely. The basic facts about Vega have been known for a long time. Its distance, its brightness, its temperature, its spectral type. These have not changed. But the margins of those measurements keep tightening, and occasionally, a new piece of information emerges, like the confirmation of surface spots in 2015 or the smooth structure of the dust disk as seen by Webb. The spots were unexpected. Vega was the first normal-type star found to have star spots, which are areas of the surface that are slightly different in temperature or brightness from their surroundings. Star spots on cooler stars like the Sun are well known. Sunspots are a familiar phenomenon, but spots on a hot, fast-rotating star like Vega were not predicted by standard models. Their detection required extremely sensitive measurements, and their cause is still being investigated. They may be related to Vega's weak but detectable magnetic field, which was itself a surprise when it was first measured. Magnetic fields on A-type stars are not common. Most stars of this type rotate too fast and have the wrong internal structure to generate strong fields. The Sun's magnetic field is produced by a process called the dynamo effect, which requires a convective zone, a region where hot material rises and cool material sinks in a churning cycle. This churning, combined with the Sun's rotation, generates and sustains the field. Vega's outer layers are mostly radiative, meaning energy is transporting by radiation rather than convection, which makes a dynamo less efficient. The fact that a magnetic field exists at all, even a weak one, suggests that something more complicated is happening inside Vega than the simple models predict. None of this is resolved. It is an area of active research, and Vega's role in it is the same role it has played for over a century. It is the bright, nearby, well-positioned star that astronomers keep coming back to whenever they have a new tool or a new question. Its convenience is its legacy. Far from here and far from now, the dust around Vega may eventually produce something. The collisions that generate the fine dust in the disk are also the kinds of processes that, given enough time, can build larger objects. Grains stick to grains, pebbles accumulate into boulders, boulders merge into planetesimals, planetesimals collide and merge into protoplanets. This is the standard model of planet formation, and it is how the planets in our own solar system are thought to have assembled. Whether it will happen around Vega depends on conditions that are not fully known. The disk may not have enough material. The star's relatively short remaining lifespan, a few 100 million years, may not be enough time for planets to form from scratch, especially larger ones. or the process may already be underway, with objects too small to detect from 25 light-years away slowly growing in the dark. There is no way to know, from this distance and this moment, what Vega's system will look like in 100 million years. The dust disk is there. The conditions are plausible, but the outcome is uncertain, and it will remain uncertain for a very long time, probably longer than any current observing program will last. It is one of those questions that astronomy can pose but cannot yet answer. The light from Vega that reaches Earth tonight left the star about 25 years ago. It has been crossing space at 186,000 miles per second since then, passing through nothing of consequence, just the near vacuum of interstellar space, with perhaps a few stray atoms of hydrogen per cubic centimeter. When that light enters the atmosphere, it is slightly bent by refraction, slightly scattered by molecules, and slightly dimmed by whatever dust and moisture happen to be in the air above the observer. What remains, after all of that, is the blue-white point that people have been namming and measuring and telling stories about for thousands of years. The photons that make up that point of light were generated in Vega's core, or more precisely, in the layers just above the core, where hydrogen fusion releases energy in the form of high-energy photons. Those photons do not travel straight out. They are absorbed and re-emitted by the dense material of the star's interior, following a random, zigzagging path that takes, on average, tens of thousands of years to complete. A photon generated in Vega's core today may not reach the surface for another 100,000 years. Once it does escape the surface, it travels the 25 light-years to Earth in about 25 years. The journey within the star takes far longer than the journey across space. This means the light arriving from Vega tonight carries information about conditions inside the star from long ago, information that has been filtered, reprocessed, and re-emitted many times over. The absorption lines in the spectrum are added only in the outermost layers, the atmosphere of the star, where the density is low enough for individual atoms to imprint their signatures. The rest of the information, the overall shape of the spectrum, the total brightness, the color, reflects the bulk properties of the star averaged over a long period. It is a peculiar kind of communication. Vega does not send a signal. It simply emits light in all directions, continuously, as a consequence of being hot and large. A tiny fraction of that light happens to head in our direction. An even tinier fraction of what heads in our direction happens to enter a telescope or reach an eye. And from that slender thread of photons, an entire picture of the star has been built. Its distance, temperature, mass, radius, rotation rate, composition, age, and the structure of its surroundings have all been determined from light alone. No spacecraft has visited Vega. No probe has sampled its atmosphere or photographed its dust disk up close. Everything we know comes from interpreting the light. That is true of almost everything in astronomy beyond the solar system. The tools have improved enormously since Bond and Whipple pointed a telescope at Vega in 1850. The daguerreotype plate has been replaced by charge-coupled devices, and then by infrared arrays, and then by space-based observatories with mirrors the size of tennis courts. But the fundamental method is the same: collect light, analyze it, draw conclusions. Vega has been on the receiving end of this process more often than almost any other star, and the conclusions drawn from its light have shaped the tools and standards used to study everything else. There is a sense in which all of modern observational astronomy is downstream of Vega, not entirely, of course, not in a way that gives Vega sole credit for anything, but in the way that a road has a starting point, even if many other roads branch off from it and go in different directions. The first stellar photograph, the first stellar spectrum, the first dust disk, the 0 point of the brightness scale, the anchor of spectral classification. These are not all the same thing, but they all flow through Vega, and they all contributed to the framework that astronomers use today. Vega will remain visible for a very long time, even as it slowly changes. Its main sequence life has a few 100 million years left. Its distance from us will shrink, then grow again. The precession cycle will bring it near the pole and then carry it away. The Lyrid meteors will return each April as long as Comet Thatcher's debris trail persists. None of these things require attention. They happen whether anyone is watching or not. The star called Diansame by the Assyrians and Jainu by the Chinese and Alpha Lyrae by modern astronomers continues to do what it has done for the past several 100 million years. It fuses hydrogen. It emits light. It spins once every 12.5 hours, its equator bulging outward from the effort. Its dust disk circles quietly, grinding itself finer with each collision. And its light, 25 years old by the time it gets here, arrives at the top of the atmosphere and filters down through miles of air and moisture and whatever else stands between it and the ground. On a clear night from almost anywhere in the northern hemisphere, you can see it without a telescope. In the summer, it is nearly overhead. In the winter, it is lower, near the northern horizon. It is one of the first stars to appear after sunset, bright enough to show through twilight, bright enough to see even from a city. It does not look like a harp or an eagle or a weaving girl. It looks like a point of light with a faintly blue-white color, steady and unremarkable, the same way it has looked for as long as anyone can remember and for far longer than that. The constellation around it, Lyra, is small enough to hold behind a raised fist. Its few dim stars are not much to look at, but within that small patch of sky, there are objects that have attracted telescopes for decades. The Ring Nebula, a shell of glowing gas expelled by a dying star, sits between two of Lyra's fainter stars. Epsilon Lyrae, a multiple star system, resolves into a pair of pairs through a small telescope, 4 stars orbiting each other in a tight arrangement. These are details that require instruments to see. Vega itself does not. It stands apart from those details, brighter by a wide margin, requiring no optics and no special knowledge to find. The Babylonians may have known it as the messenger of light. The name, if it is accurate, suggests that they saw Vega not just as a decoration in the sky, but as a carrier of information, a point of light that communicated something about the structure of the world above. They would not have known about spectral lines or photometric 0 points, but the instinct was the same. The light from that particular star seemed to mean something. It still does, though the meaning has changed. What Vega means now is different from what it meant to the Babylonians or the Greeks or the Chinese. It means magnitude 0. It means spectral type A0V. It means 25 light years. It means a dust disk, a rapid rotation, a pole pointed at Earth, a past and future pole star, a list of firsts in the history of astronomy. It means a reference, a baseline, a place where measurement begins. That is a lot of accumulated significance for a single point of light, and yet Vega does not behave as though it knows. It spins, it shines, the dust around it drifts. Somewhere right now, a photon that left its surface in the early 2000s is crossing the last few light months of space between there and here, heading toward an atmosphere it will never notice. On a planet it has no relationship to, carrying a fragment of information about a star that has been used as a benchmark for over a century. The photon carries no awareness of any of this. It is just light, moving at the only speed it knows, in the only direction it was emitted, following the same straight line through space that light has always followed. It does not care about magnitude scales, or precession, or myths about weavers and cowherds. It does not know that it is 25 years late, or that the star it came from has since rotated roughly 17,500 more times, or that the dust disk it passed through on its way out has shifted slightly in the intervening years. But when that photon arrives, if it happens to enter telescope, it becomes data. It joins the long record of light collected from Vega since 1850, and before that, the long record of light observed by eyes going back thousands of years. It becomes one more piece of the picture. The picture is detailed now, far more detailed than Bond and Whipple could have imagined when they exposed their daguerreotype plate. But it is still a picture built from light, and light alone. The star continues. The axis of the Earth continues its slow rotation. The celestial pole, right now aimed near Polaris, is moving, tracing its wide circle, heading as it always does through the same sequence of stars. Thuban, then nothing notable for a while, then Polaris, then gradually toward Cepheus, then eventually, thousands of years from now, toward Lyra, toward Vega. The same circuit it has been making for as long as Earth has had its current tilt and shape, and will keep making until something changes that tilt or that shape, which would require a force much larger than anything in the ordinary course of planetary life. The Hoover Dam Monument records one fixed point on that circle, a date in the 1930s encoded in star positions and the angle of precession inscribed in a floor that most visitors walk across without noticing. The designers of that monument understood something about the steadiness of these cycles. They trusted the cycle enough to build a clock on it, not a clock that ticks, but one that holds still while everything else moves. The position of the stars on the floor does not change. The sky above does, slowly, year by year, degree by degree. And by comparing the two, the floor and the sky, someone 10,000 or 20,000 years from now could work out when the dam was built. That is a kind of timekeeping that does not require maintenance. No batteries, no resetting, no human intervention, just the predictable, well-understood motion of Earth's axis through space, calibrated against the position of the stars. It is the same kind of timekeeping that ancient navigators used when they noticed which star was closest to the pole, or which star set at the beginning of autumn, or which part of the sky produced streaks of light each April. Vega has been part of all of these systems, at different times, in different ways. It was part of the sky that ancient people read for practical information. It became part of the instrumental framework that modern astronomers use to calibrate their measurements. It will be part of the sky that future observers see when they look toward the pole. The mechanisms behind all of this are ordinary. Gravity pulls on a bulge, an axis wobbles, a star is bright because it is hot and close, a dust disk reflects infrared light, hydrogen absorbs photons at specific wavelengths. None of these are unusual phenomena. They are standard physics, operating the same way here as they do everywhere else in the observable universe. What makes Vega notable is not that it does anything unusual, but that so many ordinary things intersect at a single point. 25 light-years away, a star roughly twice the mass of the Sun is burning through its hydrogen at a pace that will exhaust it in a few 100 million years. It spins fast, bulging at its equator, presenting its pole to a planet that has assigned it the role of reference point. Its light defines where 0 is on the brightness scale. Its spectrum defines the starting point of classification. Its position in the sky marks a point on a 26,000-year cycle that has been running since long before anyone was there to notice. The light from that star has been reaching this planet for as long as this planet has existed, 4.5 billion years, though Vega itself has only been shining for a fraction of that time. When Vega formed, about 450 million years ago, Earth was already old. The oceans were established. Life had been evolving for billions of years. The first animals with hard shells were just beginning to appear in the fossil record. Vega switched on into a universe that already had a long history, and it will switch off in its own time into a universe that will continue without noticing. In the time between those two events, the light keeps coming. 25 years in transit, arriving continuously, carrying the same information in slightly updated form, like a signal that never changes its frequency but very gradually shifts its volume. For now, the volume is increasing as the distance between Vega and the Sun slowly decreases. In a few 100,000 years, it will be at its loudest. Then it will begin to fade, not because the star has dimmed, but because the distance is growing again as two objects on independent paths through the galaxy move past each other and continue on. The star that was once called the Falling Eagle and the Weaving Girl and the Judge of Heaven and the Messenger of Light is still called all of those things in one language or another. It is also called Alpha Lyrae and Magnitude 0 and Spectral Standard A0V. Each name reflects a different way of looking at the same object, from a different time, with different tools, for a different purpose. The object itself does not change because of the names. It remains what it has been since its formation, a large, hot, rapidly spinning ball of hydrogen and helium surrounded by a disk of dust, sitting in a part of the galaxy where it happens to be close enough and bright enough for a civilization on a nearby planet to notice it, measure it, name it, and use it as a fixed point from which to measure everything else. That fixed point in the end is not truly fixed. Vega moves, Earth moves, the pole moves, the brightness scale has been updated, the spectral classification system has been refined, Nothing stays precisely the same, but the changes are slow enough and the systems are robust enough that the reference holds. It has held for over a century of instrumental astronomy and for thousands of years of naked-eye observation before that. It will hold for a long time yet. The light is still arriving.